Here are a few more examples of computing centroids. First, let's start off with the kind of silly example, silly if you think about it anyway, of finding the centroid of a line segment. So let's let C be the line segment from point A to point B. We'll use the standard parameterization for such a thing. That's A plus AB t, B being the vector that points from A to B. So you could do terminal minus initial. Think of that as B minus A. T, of course, going from 0 to 1. And should point out, of course, we're conflating points and vectors, but that's okay. This is for convenience. Now, let's go ahead and find our centroid. So first we need to find the mass. Remember, for centroid, this is constant density. The density is 1. And so mass is actually the same thing as arc length, which again, if you think about what this is for a line segment, our calculation here is kind of silly. So I need the integral from 0 to 1 of r length of r prime of t dt, but the derivative of this particular parameterization here, the derivative really is just ab, right? So all we end up with is the length of the vector ab dt, integrating from 0 to 1. That's just, keep in mind, even though it looks more complicated, the length of AB is just a number, and integrating a number from 0 to 1, you just end up getting itself, right? So, so the length of the arc length for our line segment here is exactly what you would think. It's the distance between A and B. Okay, now let's find our moments. So first, let's find the moment about the YZ plane, the moment about x equals 0. So again, keeping in mind we have constant density. This is just x ds. Okay. Now we need to integrate from 0 to 1, and here's where it's, if anything, just slightly tricky. Keep in mind that the x component of our parameterization, here's our parameterization right here, we don't have a parameterization written out in terms of x, y, and z. Right? So I'm going to just use kind of, I don't know if it's a trick, but a way to peel off the x component is just to dot whatever vector that is with the I vector, right? With 1, 0, 0. That'll pick off the x component. And then we multiply it by our ds. Okay. Well, let's use the fact that the dot product is bilinear. Use this distributive property. So we have a dot I times the length of AB, plus we have AB dotted with I times the length of AB times t dt. All right, now we need to integrate this from 0 to 1. Again, this first part right here, that's just a number, so we have, it's a dot I times the length of AB, and then we have a number, a complicated looking thing, but just a number, and times t. T integrates to t squared over 2, so we'll have AB dotted with I times the length of AB over 2, and then you have t squared evaluated at 1 and 0. That's just going to come out to be 1. So this thing is just multiplied by 1. All right, now let's figure out what is the x component of our, the x coordinate of our centroid. Well, we should take our moment divided by our mass. Let's think about, so we got a dot I plus ab dot I over 2. Both of those things are multiplied by the length of AB, right? So I just factored the length of AB out of this result here. And then mass, as our arc length, that's just the length of AB. So notice those happily cancel off. And let's go ahead and, I'm going to undo kind of part of what I did before and factor things back apart. I have A dotted, I have A plus AB over 2. Both of those things are dotted with I. Okay, so there we go. What is the x component? It's a plus ab over 2 dotted with I. Now, I'll just say likewise. The only thing that would change if we were computing y bar is we would have dotted with j instead of dotted with I. And the only thing that would change when we went z bar would be this dotted with k instead of with I or j. Now notice, we have a vector a plus ab over 2, and we have that dotted with I, with j, and with k to get x, y, and z coordinates. Well, that just means that the I, j, k components or coordinates, however you want to look at it, of this vector, well, are x bar, y bar, and z bar. So in other words, x bar, y bar, z bar is this. But if you unravel that a little bit more, again, we're conflating points and vectors, and that's okay. AB is terminal minus initial, B minus A. If you work that out, that's A plus B over 2. Well, what do you know? It's the midpoint. So again, this is all kind of silly once we realize that we found out that the centroid of a line segment is its midpoint. Of course it's its midpoint, right? We didn't really need to do a complex calculation to figure that out. All right, sometimes it's comforting to know that a complex calculation gives us that familiar result, that what we're doing isn't actually all that unfamiliar. All right, let me give you two more examples. These are ones where we take advantage of some sort of symmetry. So first of all, let's find the centroid. Again, this means you're dealing with constant density of the. Let's do right half of a circle. Let's do the circle centered at the origin of radius. I'll make it radius 3. Okay, so the right half of this circle. Right. So in other words, we have a circle whose radius is 3, but we only want to consider the right half of this circle. Okay. So there we go. There's our curve C. Okay. Well, first thing I need to find is a parameterization. Okay. So for right half, well, for a circle, keep in mind we essentially use polar coordinates. This is a circle whose radius is 3, so we'll have 3 cosine t, or cosine theta if you want to use theta as your parameter, 3 sine t for the y component. And then what we need to be careful about is the domain for t. Now we want t to only, we want this to only sweep out half of a circle, specifically the right half. And so if we think about t being the angle swept out from the positive x-axis counterclockwise, to start off at the bottom of the circle here, we need to have t go back up to negative 90 degrees. And to go up and stop here at the top, we need to stop it at 90 degrees. So t should go from negative pi over 2 to pi over 2. If we'd wanted the left half of the circle, we'd go pi over 2 to 3 pi over 2. If we'd wanted the upper half of the circle, we'd go 0 to pi. If we wanted the bottom half of the circle, we'd go from pi to 2 pi. But anyway. Okay, next we're going to need to find our ds, the length of the derivative. And so this, I'll skip the details, just comes out to be 3. The derivative of r is negative 3 sine, comma 3 cosine. You square, sum, square root, you end up with 3. Okay, so that's, we have our ds. Now let's go ahead and start calculating stuff. Something I probably should have started with is mass, right? Keep in mind that mass is just arc length. And so this is half of a circumference of the circle. So we know that all that is pi times the radius. So we actually didn't need to do anything here. We didn't need our parameterization or ds to figure that out. We got this basically by geometry. And you should always see, can I find something via geometry? Let's ask, can we cut down our work because of symmetry? Right? Does symmetry tell us anything? Well, certainly it does. If you look at our curve here, notice that wherever the middle of it is, it's definitely split in half by the x-axis. what that tells us is that y bar is going to have to be 0 if we want this thing to balance. So notice we've already gotten m and y bar, and thus also the moment about the x-axis. We've gotten those things just for free by geometry and by symmetry. All right, so we can't, though, necessarily guess the x-coordinate with geometry and symmetry. That we're going to have to actually break down and do an integral. So on our way to find the x-coordinate, we need the moment about the y-axis, i.e. the moment about x equals 0. So this is the integral along our curve of x ds. So we're aiming at trying to figure out what the x-coordinate is. Well, we plug in our parameterization. We go from negative pi over 2 to pi over 2. The x component of our parameterization is 3 cosine t. ds is 3 dt. So we end up with 9 times, and then we have the integral from negative pi over 2 to pi over 2 of cosine. So if you keep in mind, here's just a trick worth remembering. With sine and cosine, half of a hump has area 1, right? So if we want cosine from the area under cosine from negative pi over 2 to pi over 2, its area is actually 2, because we have a full hump of cosine. And so that gives us an answer of 18. If you don't like that, you of course could integrate the integral of cosine as sine and evaluate it at pi over 2 to negative pi over 2, and you'd eventually get that the answer is 9 times 2, but this is easier. All right, finally, x bar is moment over mass. That's 18 divided by 3 pi. So in other words, this is 6 over pi. Now's a good time to reflect on our answer. Does this even make sense, right? So we've found that x bar, y bar is 6 over pi, comma 0. 6 over pi, pi is about 3. This is about 2. And so let's think. We have our circle, our half circle of radius 3. So here's 0, and then maybe 1, 2, 3. And we found that the center of mass, the centroid, is right there. And that actually seems pretty reasonable, right? You kind of think of how much stuff is to the right and the left of that and how much is below and above that. That does seem to be kind of the middle. So it's a plausible answer. All right, and it's also the correct answer. Let's do one more problem, one more example, also taking advantage of geometry and symmetry. Let's do a quarter circle. Okay, so this time I want x squared plus y squared equals 9. We'll use the same circle, but let's make sure that x and y are both non-negative. This is the part in the first quadrant. Okay, and so again we're finding a centroid, and that means we have constant density. Okay, so before doing anything else, let's see how far we can get with geometry and symmetry. Well, geometry, we know that the mass, which is the arc length for a centroid problem like this is just a quarter of the circumference of a circle, so that would just be 1/2 pi times the radius, right? So we get this as 3/2 pi. Well, that was easy. Okay, symmetry. Okay, well, this time we can't get either coordinate by symmetry, but we can say something, right? So we're dealing with a quarter circle, right? Here's our quarter circle here. Notice that wherever the middle is, the x and y coordinates are going to have to be the same, right? That's what symmetry tells us this time, is that the center, wherever it might be, has to lie on that line y equals x. So in other words, we can choose whether we want to find the x-coordinate or the y-coordinate, and we'll get the other for free. It doesn't really matter, but let's go ahead and find the x-coordinate. Okay, so now we'll on our quest to find the x-coordinate, in other words, we have to find the moment about the y-axis. Now we need a parameterization. We'll borrow essentially the one from our previous problem, same reasoning behind where this parameterization comes from. Although now we have a quarter circle, so I'll let you think through why this should be 0 to pi over 2 for a quarter circle, in the first quadrant anyway. And then we need our ds, It's the length of r prime dt, and of course is the same as before because we only changed the domain on our parameterization. All right, what's my? It's the integral along our curve, x ds. This is the integral from 0 to pi over 2, and now we have 3 cosine of t times 3 dt. This is 9 times, and this time we have but 1 half hump of cosine, right? And so this is just 9 times 1, so in other words the moment is just 9, and that tells us then that x bar is 9 over 3 halves pi. In other words, 18 thirds pi, or 18 over 3 pi, which is 6 over pi. What do you know? It's the same as before. And then we'll use our symmetry argument to get that that's the same as y bar. So what's our centroid? X bar, y bar is 6 over pi, comma 6 over pi, which again is about 2 comma 2, which is about right there, and that makes pretty good sense.